Okay, hi everybody. So today we're going to do the second to last section in calculus. How exciting! Calc 1. So we're going to be talking about the substitution rule. Now this rule for sure we'll always use for all your calc series. Even beyond that, I still use it, I mean, not just because I'm a math teacher, but because, you got to use it. So what the substitution rule is, it's basically the way, okay, so remember when we were doing derivatives and we have that chain rule when we have inner functions? And now what the substitution rule is going to allow us to do is when we have things inside our function that are composed of other functions, then we can do kind of like this backwards chain rule kind of thing. And the substitution rule is going to let us do that. So let's say we want to integrate this function here, which is the integral of 2x times the square root of 1 plus x squared dx. Okay, so far we've learned some simple integration rules. We've learned how to do them using Riemann sums, which is the way they were originally shown to do. And then we learned about antiderivatives, and we did it this way to find the area under the curve. Now, we've learned simple integration methods like the backwards power rule method. And we also recalled that the integral of, for example, let's say sine is negative cosine, and that's because if we take the derivative of negative cosine, we will get back sine, positive sine again. So we've learned a couple of those tools before that, but we still haven't learned how to deal with something like this. We can't really do a power rule here because we have like this multiplication going on, and I don't know, it's just kind of crazy. So what I'm gonna do is I'm gonna start with this example. Now, if it doesn't make much sense right now, that's okay, because I just wanna show you how we're gonna go about that substitution rule, and then we're gonna lay down the law on the substitution rule, and then we'll go through more and more and more examples, okay? So let's say we wanted to integrate this. Then how would we do this? So what I'm gonna do is, just bear with me, just pay attention, and I promise you, you will get it. Okay, so what we're going to do is we're gonna let you, and like I said, just bear with me and watch. I'm gonna let u equal 1 plus x squared. So what I'm letting u equal is this inside piece right here. Not a coincidence. And then what I'm gonna do is I'm gonna take the derivative of u with respect to x, but I'm gonna write it like a differential, like we have done before. I'm gonna write that the derivative of u is equal to du, and then the derivative of this with respect to x is just simply 2x dx. Okay? And I'm gonna put a little cloud around this because I am cute. What? Okay. And so now okay, maybe that was too obnoxious of a cloud. Okay, so I'm just gonna circle this over here. And so now what I'm gonna do is, since I let u equal this inside piece right here, what I want to do is I'm going to actually substitute that in for my integral. So I'm gonna let u be inside here. Now, just watch. So we're gonna do the integral. Now I have the square root of u. So we all agree that this part here is this part here. So far so good. But now I have to do something with this. Like, why would I even do this? So the reason that I did this was because here I have a 2x dx, and here I have a 2x dx. And I can't integrate this as it is right now. Like, I can't do the integral of the square root of u times dx. Because I can't integrate u when I'm integrating with respect to x. That makes no sense. That's why I said you always have to be careful with what variable you have here. Dx does not make sense to have there because we want to integrate u to make our life a lot easier. So good news is that we have a 2x dx, we have a 2x dx here, and we have that du equals this 2x dx. So what we're going to do now is we're going to write, this is going to equal the square root of u du. And I'm just putting things in red that I replaced. And so all I did here was now we made a substitution for this u. So this part was pretty simple. And now I replace 2x dx by this du. So basically what we're doing here is we're kind of rewriting it in a different method, but all our pieces are still here. Remember, this is equal to 2x dx, and the inside part here is equal to 1x squared. Why isn't it writing? Oh, there we go. And 1 plus x squared. So in reality, they're still there. Now they're just with a different variable, and which is like awesome because now I know how to take the antiderivative of this. I know how to integrate this. Now I could rewrite it. I mean, you could take the antiderivative as it is, or you could rewrite it if it makes your life a little bit easier. As, oops, not x, as u to the 1/2 du. And now I'm integrating this integral with respect to u, and all my variables are u. So I could easily just go ahead and do it. So if I integrate this, right, we're going to add 1 to the exponent, do that backwards power rule, and then divide by the new exponent. I add 1 to the exponent and I'll get 3/2. So this is going to equal u, 3/2. Then I divide by that exponent. So I'm basically multiplying by that reciprocal there. And then we can't forget our plus c here because right here we have a indefinite integral. We don't have a definition for any of these. All right, beautiful. Now our last step for this is that we are going to substitute back in what u is equal to, because our whole goal was to integrate this, and this is with this has x variables all over it, so I can't leave this like this because that would be wrong. So now I'm going to take my u and plug it back in here, okay? So seems a little bit iffy, but you know, bear with me, and then we'll lay down, like I said, the law on all the steps on how to do this. And I'll show you even some tricks on how to do it. So now if I replace u by my 1 plus x squared to the 3/2 plus c, then I'm done. This is my answer. But what? That's, why do I have a u there? Okay, there you go. So this is my answer, the 2/3 there. Okay, and so like I mentioned before, when you're first learning this, you want to make sure you're doing it right. So how would you know that you're doing it right? So the good thing is that you've all become experts at taking derivatives. All of you have. So what I want you to do to check this is I want you to take the derivative of your final answer and make sure that you get this top one. And so I'll do it over here on the side just to keep it on the same page. So I'm gonna over here, let's do a little box. I'm gonna check that the derivative with respect to x, and I'm only gonna check this once just so that you guys remember that this should be a tool that you use when you're first learning to use on your homework, on your exams, on your quizzes, until you're very confident with these methods. U substitution can be a little bit funny sometimes, so it takes a while to get used to. Okay, so now if I take the derivative of this, right, here I just have like a power rule, bring it up to the front with a chain rule, right? And that's why we had to use the U substitution. And so if I bring that forward, I'm going to get 2/3 times, here I'm taking the derivative, so this is going to be 3/2. Bring that power up front, subtract by 1, which is going to be 1 plus x squared times raised to the 1/2 power. Now I multiply by the derivative of my inside, which is x squared. So I need to multiply everything by 2x. Perfect. And now this just goes away. Boom, boom. And we get 2x times 1 plus x squared raised to the 1/2 power, which is the same thing as 2x and the square root of 1 plus x squared. Which, isn't this the same as that? Well, it is, isn't it? Interesting. that's how you're going to know that you did it right. So always check them. And for the rest of the examples, I'm not going to take the time to check them because it's going to take a while. And I don't want to make a super long video, and I'd rather have more examples. But you should always, always, always practice checking them yourself, especially in your homework and especially on an exam. Okay, so now that we did an example, it's okay if you were still really iffy about what was going on there. Perfectly normal, because we just learned something new and it was kind of like, what did you just do, right? Okay, that's okay. Now now that we've gone over an example, I can give you the substitution rule, and now maybe that example might make a little bit more sense now. And then we'll do a few more examples. So the substitution rule says that if u is equal to g of x, which is that u sub that we did in that last example. So for example, in that last example, our u was 1 plus x squared. If that function is differentiable, and we need it to be differentiable because as you notice that we had to take the derivative of u over here. So it needs to be differentiable. Whose range is an interval I, and f is continuous on that interval I, then the substitution rule says that if you have a function that's composed with another function, so you have some function f that's composed with another function, which is just like Goff or fog, right? Those compositions of functions multiplied by the derivative of the inside, and I'll show you exactly what we mean by this over here. Then we can just integrate f of u du to make our to make our integration a lot easier. So yeah, let's do this. So a few remarks on this is, let's lay down some remarks, is that the substitution rule is often used to reverse chain rule. So it's often used to reverse chain rule, which is the purpose of it. So remember that chain rule was a function inside a function, and when we took the derivative of function inside a function, we applied that chain rule. But I want to make some remarks about this, is that the challenge to this is really just getting used to it, but the challenge is choosing the appropriate u. This takes practice to get intuition for what to pick. Okay, so what this is saying is, okay, yes, we know this, the substitution rule is used to reverse chain rule. But the challenge for u sub is kind of the same challenge, a little bit different of when you were learning chain rule. You know how sometimes you had to do chain rule, or I don't know, things just got weird, and that's normal. The challenge is picking that appropriate u, so that u value, that inside function. And the good news is that I will show you some very common ways to be able to find that u value, but most of the time, this comes from practice, 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 so that you can build up intuition on what to pick. Now, I used to hate it when I was a student, when my calc teacher would tell me, because I would do a problem, I would get stuck, I would go ask for help, he would tell me how to do it, and I was like, well, how did you know that? And he would say, from experience. And I was like, are you serious? But until I became, I started tutoring calculus and tutoring higher level math, and then I became teaching it, and I realized, and the more that I learned higher level math, I realized that a lot of your intuition does come from experience. So you just have to do a lot of these practice problems, and then you'll know what to pick. But at first it is a struggle. So always come for help, because, you know, through this, the best way to go about this is you practice, practice, practice problems, just like you did when you were learning derivatives. Same thing. practice problems. So now let's write out the steps for how to do this, and then we'll do a bunch of examples. So let's do some steps. So these are pretty common steps that you can basically follow that might help you do this. Okay. This will be on your final. So you're going to choose, first of all, u, and that might be a challenge of its own. Then you're going to calculate. I guess I should be numbering these, right? So first you're going to choose u. 2, you're going to calculate du, which is going to equal u prime x dx. So you're basically just differentiating u with respect to x, moving that x over, just like we did with differentials. And then you're going to do, your next step is to substitute, of course, because that's the whole reason we're doing u sub, to substitute back into that integral so that we can have a simpler function to integrate. So we're going to substitute in du over u prime of x. And you didn't really see this yet. That notation might be a little bit funny. But when we do examples, it'll make more sense. So in 4 dx, that's a dx. Wow. dx. It's a dx. And write the remainder for the integrand in terms. So what we mean by the integrand is just that thing that you're integrating. So for example, in this one, this was our integrand. Oops. In this one, this was our integrand. Sometimes this thing lags. I'm so over this. Okay, so that's all it is. And then once we finish taking the antiderivative, so our fourth step is going to be to solve the new integral in terms of u. And then our fifth step is going to change back like we did in the last one in terms of x. Okay, so first step, pick u. Second, calculate the derivative of u with respect to x. We're going to substitute in, then solve that nice, easier integral. And once we solve that and we have the answer to that integral in terms of u, we're going to change it back to x, okay? And so let's do a few examples. There's actually a lot of examples that I picked. They were all just so good. I just couldn't just pick some, but we'll do a few. And yeah, it should be fine. So let's do this one. So let's do a few examples. Maybe if I have time during the week, I'll add more. But the best thing is for you to do your homework, take your time on your homework, and come to my office hours. Okay, let's not forget my dx. Okay, why isn't it showing the top part? Okay, there it is. Okay. So let's say we wanted to integrate this whole function. Now, it wouldn't be the smartest idea to multiply this out 100 times, right? And then take the antiderivative. That would take way too long. So what we're going to do now is we're going to pick our u. So how do we pick our u? So our u is usually the thing that's trapped inside parentheses, a square root, or some trig function. So in this case, what you're going to pick as your u is going to be 2x plus 3. That's going to be what we're going to pick as our u. And I'm going to write u on the side here. I'm going to do all my calculations for u on the side. And I'm going to let u equal 2x plus 3. And now our next step, so this was like our first step, is to pick your u. Your second step was to basically pick, take the derivative of u with respect to x and write it in terms of du times u prime times dx. So if I take the derivative of u, I'm going to write du is equal to, now the derivative of this with respect to x is simply 2, and then I can't forget my dx, right? So we just took the derivative of this. And so what you want to do now is you want to be able to substitute it back into that function. But when you do that, we have to be a little bit careful. I want you to think of integration by substitution as like finding your missing puzzle pieces. So this is going to be your puzzle over here, right? This is your goal to try to integrate this. But in order to integrate this is you need to switch it back in terms of u. So right now, as it stands, I have something to replace the 2x plus 3. That doesn't matter right now because when we differentiate that, we know how to do the integral of that. And so we have to replace, basically you're trying to replace all your x's, all your old variables, anything that involves that x. So in this case, this is what we're trying to replace. And now we need to replace this dx by du. But notice something, there's a 2 with this dx, and I don't want that. I want to replace dx, not the 2 dx, right? So what you're going to do in this step is you're going to move that 2 out of the way, and the way we do that is by dividing over by 2. And so then we're going to get 1 over 2 du is equal to dx. And now we have something for the 2x plus 3, and we have something for that dx value. And now we can just substitute it back in. And then put our little crowd around it so that we know what we need to substitute back in. So it's like a puzzle piece. You replace your dx, anything that involves x, in here. And so now we're going to go ahead and integrate it. So we're going to do the integral. Now, this was our function. And now what was in that function was 2x plus 3, but now we're going to replace it by u. And now we're going to replace dx by 1/2 du. So we're going to replace this by 1/2 du. Now I'm just showing you this part here. This is normally not the way that I do it, but I want you to see where I'm plugging things in. So this is everything that's getting replaced by what we chose to substitute. And so now what I'm going to do is, I don't like the way this looks. It just makes my brain hurt. So I'm going to go ahead, and since we have an integral, everything's just getting multiplied out. This is like a constant, so I'm going to just move it out over to the front. This is going to be 1/2 times the integral from u to the 100th power times du. Now it looks a little bit nicer and doesn't hurt my head too much. So now all we have to do is we have to integrate this, which you know how to do this. This is just a backwards power rule. So let's go ahead and apply that backwards power rule. So we're going to do 1/2 times, okay, we add 1 to that power, so it's going to be u to the 101 power, so ridiculous, plus c, right? But then we also still have to divide by the 101. Don't forget that. Okay, 101. Okay, so now what we're going to do from here is now we can plug in, we can distribute that 1/2 over inside. And so if we distribute that 1/2 inside, we're going to get 1 over 202 u to the 101 power plus c. But we're not done yet, because remember, we were trying to integrate this, which is in terms of x, not u. So now I'm going to go back to what I let u equal, and that's why it's nice to put it in this little bubble or a box or whatever you like, a heart, whatever. It doesn't matter, so that you know like where your u was. And so now I could just bring that back in, so you're not losing anything. So now we're going to go 1 over 202 times 2x plus 3. I'm just substituting that u back in to that 101 power plus. Now let's do another example. These are just going to be examples on examples on examples. And then we're going to do it using a definite integral. Same process, just have to account for a little bit of more. We have to account for something extra when we do definite integrals. But for the most part, it is the same process. So don't worry about that too much just yet. Okay. So let's do more examples. So we're going to get the integral of x squared plus, times x cubed plus 5 to the 9th power dx. Perfect. Okay, so now let's just start to integrate it. As is, we can't integrate it. There's no rule that we have for this unless we multiply this this whole thing here over and over again 9 times and distribute that x squared, which nobody has time for. Nobody. And that would be way too much. So now we can do u substitution. So like I said earlier, the thing to pick for u usually is the thing that's trapped inside parentheses in a square root in a trig function, so that you have a function inside another function. Okay, so here our u is going to be this inside piece right here. So I'm going to let u equal x cubed plus 5. And I probably like, what do we do with this? All right, just wait and see. Just wait. Remember, the goal is to be able to substitute everything that you have in this integral in terms of u. That's your goal. Get rid of all the x's, write them in terms of u. And so if we take the derivative of u over here with respect to x, we're going to get du is equal to, the derivative of that top part over there is 3x, why isn't it writing? 3x squared. The derivative is just 0, and now we have to write dx. Okay, cool, because we were just able to replace this, have something for dx, and now look at, we have an x squared and an x squared over here. So the only thing we need to get rid of or account for is this 3 that's kind of bothering us over here. So what we're going to do is, again, divide that out because we don't need him in our x squared dx, that's the thing that we want there. So we're going to write 1 over 3 du is equal to x squared dx. And so now we're able to replace this by this and this. And so now we get the and then x squared dx got replaced by 1 over 3 du. I'm going to bring that 1 over 3 over to the front now. And now I'm going to write u to the 9th power. So we replace that. And now x squared dx got replaced by 1/3 du. I have the 1/3 over here already. And so now this is going to be du. And so now we can integrate this. So if we integrate u to the 9th, we're going to get u to the 10th power divided by 10 plus c, because we're dealing with a definite integral here, so we need to write that plus c. We don't have upper and lower bounds. So, and now after that, we can distribute that 1 over 3 in, which is going to be 1 over 30 u to the 10th power plus c. But remember that our function was in terms of x and not u. So we're going to replace our u by what we substituted in for, which is going to be 1 over 30. And then u equaled x cubed plus 5. So now I'm substituting that back in, plus c. And that's our answer. Easy, right? So again, this is going to take lots of practice. Let's do, actually, I'm gonna stop here because this video, I have a feeling, is kind of long. And then we'll go on and do more examples. There might be 3 parts to this, and it's only because I know that it might seem like really long, but I think it's a good idea to do a lot of these examples so that you get really used to them, okay? I'm gonna stop this video here, and I'll see you in the next one.